Hi, it's Mr. Baker here. Today we're going to be looking at Newton's third law. Okay, so in previous lessons we've looked at Newton's first law, we've looked at Newton's second law, and in today's lesson we're going to be looking at Newton's third law, and we're going to be trying to answer these questions by the end. As an example of Newton's third law, so what is the force that keeps the moon in orbit around the Earth? Do you think the Earth pulls on the moon? Does the moon pull on the Earth? Which one pulls with greater force? Now, I want you to think about the answers to those. You might even want to pause the video now, just have a little think about those. You've probably got an idea of what the answers are. And then at the end of the lesson, I want you to think about those again and see if you still agree with what you thought at the beginning. Okay, so what is Newton's third law? So we know from Newton's first law that when there is a force on an object, it will accelerate, decelerate, or change the direction of an object. If the resultant force on an object is zero, then it will carry on doing what it's doing. It'll either stay stationary or it will carry on going at a constant speed. And we know that Newton's second law relates the force and the acceleration with the mass. So for the greater force, for a constant mass, we will have a greater acceleration. And if we have a constant force, every time we increase the mass of the object, then the acceleration will decrease. Now, Newton's third law basically says that a force can't exist by itself, can't exist on its own. There's always a second force acting against it. So this is the basis of Newton's third law, and it basically says that if object A exerts a force on object B, then object B will exert an equal but opposite force on object A. So you've probably heard of Newton's third law, and you've probably heard of the fact that every force has an equal and opposite force, or every force has an equal and opposite reaction. And that's basically what it's saying here. Every force has an equal force, but in an opposite direction, but of the same type. So if I push on an object, that object will push back on me with exactly the same type of contact force that I'm exerting on that object, but just in the opposite direction. We call these forces sometimes action-reaction pairs. So let's show you an example. So here we've got Mel on her computer, and the computer is pulled down by the force of gravity, and that causes the computer to have weight. So although the table exerts an equal and opposite force pushing upwards on the computer, the force that's pushing up isn't weight. So without the table, then yes, the computer would fall through, and the weight pushing down on the table causes a force, which would be a contact force on the table. The table does then cause a contact force back on the computer, but the actual force of weight, the table doesn't pull on the computer in the same kind of way. The table isn't causing the weight of the computer. So what's causing the weight of the computer? Okay, so this is the force that we'd have. So this isn't a Newton's third law pair. We haven't got an action-reaction pair here. We've got two forces, but we've got, and they're equal and they're opposite, but what they're not is the same type. We've got the weight caused by the computer pulling down, and we've got the reaction force because the computer is touching the table, and that's pushing back up. And they happen to be equal, otherwise the computer would fall through the table, but it's not an action-reaction pair. So what is causing the weight of the computer? Well, it's this thing, isn't it? It's the Earth. So the computer pulls the Earth towards it in exactly the same way as the Earth pulls the computer towards it. Now, we don't really think about that, and this is one of the things that actually, when we're thinking about Newton's second law, if I was to drop something, drop a pen on the floor, now the pen would accelerate towards the earth, wouldn't it? But actually the earth would want to accelerate towards the pen as well. There would be the same force, the weight of the pen, so the mass times the gravity of the pen pulling, but there's pulled down because of the earth, that would pull up towards the pen in the same way. So the earth would be pulling up towards the pen in exactly the same way. But actually the inertial mass, so the amount of mass that the pen has got is a lot smaller. The mass of the pen is tiny, the mass of the earth is big. And we know that Newton's second law says that if you've got the same force but you've got a greater mass, then you're going to accelerate less. So the reason that the pen falls towards the earth and the earth doesn't fall towards the pen is because the pen has got a lot smaller mass, and so it's accelerating a lot greater than the earth is towards the pen. But it's got an equal force. This is what it's quite a short description today, and hopefully it's just made you think a little bit about some forces. But this is what you should be able to do by the end of this lesson. You should be able to use arrows to represent direction of forces. So we've looked at that, and give examples of contact and non-contact forces. You might have to do a little bit of revision to do lots of those, but we've talked about a few today. You should also be able to describe examples where the motion of an object acted on by two forces along the same line is changed by the action of the forces, and explain that forces always come in pairs that are of the same type and equal and opposite. And that's the main thing. That's basically what Newton's third law is. Okay, so how about these questions we started off with at the beginning then? So what is the force that keeps the moon in orbit around the earth? So, well, we would talk about gravity, wouldn't we? We talk about gravity. Gravity is a property because of an object's mass. The force that's pulling the moon to the earth is because of the weight of the moon. It's just the same as my pen. I would drop my pen towards the earth, and that would have a weight. The moon has got a weight, and so it's basically being pulled towards the earth. Does the earth pull on the moon? Well, that's what we just said. So yes, there's a weight that is pulling the moon towards the earth. Does the moon pull on the earth now? You probably said yes as well, I would have thought. And you're right. The moon does pull on the earth. But which one pulls with the greater force? Now, I imagine that you probably said at the beginning of this video that the earth pulls with a lot greater force because it's got a greater mass. Now, that's quite a reasonable thing to say. That's probably what we would have all thought. It's kind of what the intuitive thing is to say, that the earth is a lot bigger, it's got a lot more mass, and so it's going to have a lot bigger force. But from what we've just talked about, Newton's third law, the force that the earth is pulling the moon towards it is exactly the same as the force that the moon is pulling the earth towards it as well. Now, why is it that the moon is the one that's pulled in orbit around and spins around the earth, and the earth doesn't do the same thing? Well, they actually kind of do the same thing, but the moon is a lot smaller. So the moon is the one that does the moving, or the vast majority of the moving, and the earth doesn't move as much because it's got a lot greater mass. But the actual forces pulling on both of them are exactly the same, and that is an action-reaction pair. That's an example of Newton's third law, where we've got an equal and opposite force, which is the weight, pulling both of those things together. Right, well, that was Newton's third law. Over the last few videos we've looked at Newton's first, second and third law, and so that's those ones done. This part of the forces of motion topic, and I've been Mr. Baker, and that's the end of this one, and I will see you next time. Thank you.